So, Professor Strevens, if we could start with Popper and then, of course, the unfalsifiability principle. Now, anyone could, I don't think it's that hard, even for a layperson like myself, to just Google what it means and get a very elementary understanding. So perhaps you could firstly just explain what the Karl Popperian unfalsifiability principle is, but then also, as you've done in the book rather well, maybe lay down some of your criticisms of it, just for the audience.
Yeah, sure. So Popper thought that really the heart of the scientific method was this very simple idea that if a theory makes a false prediction, it has to be wrong somehow. And Popper thought at the core of scientific inquiry was the systematic elimination of all of the false theories. And notionally, of course, you could imagine one day having eliminated them all and just having one true theory remaining, although, as Popper was understood as well as anyone, that was not a realistic prospect. But he thought we could at least think of ourselves as making progress by eliminating the false theories. So the thing that makes that... Oh, go ahead.
No, I was just going to ask, please continue. I want to kind of follow up on that, but keep going. Yeah.
Okay. So the thing that makes that, though, now turning to where he begins to run into difficulties, and he had plenty of things to say about these difficulties. It's not as if this is some sort of one-shot undermining of his view, but it's really difficult when a theory does make a false prediction to figure out whether it was really the theory's fault or not. Science is such a complicated thing, and in particular, the kinds of measurement apparatus that are used to make observations in cutting-edge science are often very complicated, fragile things that only work when conditions are exactly right. 99.9% of the time, when you get a false prediction, it's not really the theory's fault at all. It's just that something went wrong with the apparatus, or maybe you made a false assumption when you were making your calculations, or maybe even, and this does happen, there's an error in the software that you're using to analyze your results. And so it's not really the theory's fault or not, and it would be a terrible mistake to throw away the theory just because you got this false prediction. So if you're going to capture the spirit of Popper's proposal, you have to figure out some way of deciding when it's okay to just say, oh, something went wrong with the apparatus, and when you should say, oh no, this time it's the theory's fault, and so we've falsified the theory, as he says. We can throw away the theory. Sometimes, of course, you can just see that something went wrong with the apparatus, like, it's smoking, making crackling noises. Yeah. But often, in many cases in the history of science, we have results that were anomalous and looked like they caused problems with theories, and we'll never know what went wrong because it's just too late to go back and check. I'm sure we'll probably end up talking about some examples later on, but this Popper really never fully satisfactorily answered this question of when it's okay to blame the apparatus or other assumptions and when you should blame the theory. I think he had interesting substantive things to say, but he didn't succeed in writing down what he was really after, which was a kind of a systematic calculus, if you like, for making these decisions, something that took these decisions out of the hands of scientists who might be indulging in motivated reasoning, trying to see their own theory in a good light, and just sort of said, no, you must follow this logic, and this logic says your theory is wrong.
Yeah, because I haven't read his book where he introduced the principle, what's it called, the logic of science, I believe, but
logic of scientific discovery, it's called.
That's it. Yeah, I haven't read that book, although my understanding, again, at a very elementary level, is that it seems that Popper really wanted some kind of a priori principle or even theory of science that allows scientists to do science. And then what you would argue for, and many others, would be that, oh, well, unfortunately, for better or worse, let's say, we haven't found that.
Yeah. And so what you in fact have is, I kind of made it all sound more like a philosophical argument, but the fact of science is you have real arguments over these things, whether probably a result is just an artifact of some problem with the measuring apparatus, or the theory really is in trouble. In fact, that's almost more normal than any other state of affairs. So typically the scientists who performed perform the experiment will trust the apparatus more than the scientists sort of a few labs over who weren't there to kind of see it all operating and so on. And, in the end, if scientists keep going for long enough, there does seem to be a kind of a consensus that forms. The experiments get done enough times by enough different people. It's not as if we're just totally at sea, but it doesn't have this simple, crisp, objective, algorithmic feel to it that Popper was really reaching for.
Yeah. Well, I guess that leads us to, I don't know if I should call it the antithesis, but at least let's say we'll juxtapose Thomas Kuhn's theory, the paradigm shift, the term that he popularized, with the Popperian principle. So the Structures of Scientific Revolutions, perhaps my favorite book on philosophy of science. Yours is a healthy contender.
I'll take that.
So in contrast to Karl Popper, Professor Strevens, how does Thomas Kuhn differ? Because he came after Popper, isn't that right? So, and what were his views? Yeah.
So Popper wrote his book in the 1930s, and Kuhn wrote his book in the 1960s, to give you some sense. So Popper is in a way essentially interwar, I suppose we would now say, and Kuhn is very much post-war.
Yeah.
And Popper was still kind of firing on all cylinders by then, but he wasn't presenting whole new ideas. Well, he was entitled to kind of have a break. So Kuhn's idea is actually, it doesn't dispense with the idea of a scientific method, as I was saying earlier, but rather the idea is that at any particular time period, a science, say like particle physics or molecular genetics or economics, maybe microeconomics, will have a particular method, a particular set of rules for doing science, and actually a rather comprehensive set of rules for doing science. But that these methods are not fixed for all time. In fact, they change in episodes from time to time in dramatic episodes called scientific revolutions. Or the phrase that Kuhn famously popularized for this is a paradigm shift. And the paradigm here is this kind of big method for doing science. And when it shifts, that means the old paradigm has crumbled and a new one comes along and replaces it. So whereas Popper and the sort of classic searchers for a scientific method were looking for a single rule that is valid for all time, as you said, hopefully a priori, one that we can just know is right with certainty. Kuhn thought these methods only last for a while, and then their scientists actually push them to the point where all of their flaws are exposed, because they're very rich, but they're also kind of limited. They have a lot of assumptions built in, and inevitably some of those assumptions will turn out to be wrong. And so scientists push them to their breaking point, and in effect they destroy their own methods by exposing the faulty assumptions or whatever. And then some new method has to come along and supplant the old method. A new paradigm comes along and supplants the old paradigm. That's a paradigm shift. That's a scientific revolution. Then you have a whole new methodological complex governing what scientists do in whatever area of science it is.